Hello, everyone. Standardization is the backbone of modern aerospace. But how do you achieve it in an industry with multiple production sites located all around the world? Today, we are pleased to present our framework for industrial geometrical capability assessment. We'll explore how we synchronized our processes across all our locations to guarantee the same data-driven quality. First, a quick word about who we are. I'm Caroline Legal. I work for Airbus. I'm expert in applied statistics for manufacturing and operations.
Hello, good afternoon all. I'm working in Airbus Manufacturing Engineering Central team, and I am leading the Manufacturing Capability Database project called also MCDB.
Hello, I'm Julie Gachon from Airbus Helicopters, and I am as well Industrial Tolerancing and Measurements Engineer, and I am co-leading the MCDB projects for Airbus Helicopters.
And hello, I'm Sophie Cuvillier. I'm data scientist at Hippo Innovation, and I will be the lead GSL developer on this project.
So Airbus is a global leader in aeronautics, space and related services. The headquarters is based in Toulouse in the southwest of France. Airbus operates in more than 180 locations worldwide. Airbus activities are divided into 3 segments: commercial aircraft, helicopters, and defense and space. And Airbus maintains a presence on every continent.
Few words about Hippo Innovation now. We are a statistical consulting firm that was founded in 2007 by François Bergeret, who was a PhD in statistics. Our headquarters are also located in Toulouse, in France. And today we are a team of statisticians and data scientists with skill in metrology, SPC, AI, machine learning, JMP, and of course, statistics. We are, by the way, a JMP partner. We have already developed several tools like GAT for outlier detection, Yeti for yield optimization, SHAM, which is also a tool for outlier detection, but for time series analysis. But we can also do software on demand, like we are doing for Airbus, for instance, because we can code in various statistical language like GSL, Python, R, and so on. And finally, we can do consulting and training in all Europe on various subjects like DOE, SPC, and so on. I will now hand over to Julie that will explain you the context of the project.
Yes, for you to have a more deep understanding of what is the purpose of our solution, I would like to explain to you that in Airbus we have a design office that is providing a set of drawings with target and tolerance values, defining the product to be produced. And then we have production that is taking those drawings and validating the values on the drawing, the tolerances. To give you an idea of magnitude, an aircraft is approximately 80,000 of those tolerance values, and it is really important that we have the right one the sooner possible. And if not, we would be facing costly quality issues, especially if they are detected too late. So this is the compromise that needs to be done, but most of the time it's not an easy discussion. On one end, we have design office that is aiming for tighter tolerances to get better performance. And on the other end, we have production that prefers looser tolerances to reduce the lead time and the production cost. The discussion between the two is most of the time supported by their experience and no factual data. And MCDB's purpose is to help us navigate this conflict based on factual shared data. I will now hand over to Hélène to explain to you the workflow.
Yes, thank you, Julie. For some years now, we are developing process, method, and tools to answer the core conflict presented by Julie. So we need to support properly the co-design activities with the geometrical capability, and it is really needed for our target to achieve the right first type design. So to gather the data in our database, we define a workflow of the following workflow. As you can see in the screen, the MCDB solution use different digital tools at every step of our workflow. The first step is the scoping, so part selection, characteristic identification. For that, it is manual. It doesn't require any specific software. Then, for the second step, which is data collection, we use Skywise, which is our data lake, to gather the data. It captures both the measurement data, but also the context data, the one related to the product, and also how we made it industrially. Then we move to the part that is statistical analysis. This part is done with JMP software, and we will develop it today. Then finally, we store the result in AWS. This keeps the data organized and make it easy for us to access and review later. With the next slide, I will introduce the definition of the industrial geometrical capability, and then Caroline will present some examples. So when we want to secure the quality in time, we need to work on two criteria, the variability and the centering. To improve the quality, first, we work on the variability of the process, and then we center on the target. For the first step, the first step is about ensuring a stable process, a process under control. For that, we need a key criteria, and that's our IGC1, which is in fact the statistical spread in which we have 99.7% of the value. For a Gaussian distribution, it is 6 sigma. For a non-Gaussian distribution, we need to work with percentile. With simple words, the IGC is the achievable tolerance interval with a perfect setting. So key point to notice, for IGC, we do not need a specification interval. We can calculate an IGC without having a specification interval. Then to go to our next step, which is providing the tolerance interval for the code design, we need to consider the IGC1, which is the variability, and also we need to consider our ability to recenter the mean value to the target. So it's not provided by the IGC, but it is another topic we are working on.
So, as explained by Hélène, the industrial geometry capability is about dispersion of a distribution, so it's about statistics. Every geometric characteristic, such as a diameter or a position relative to a reference, is driven by a physical phenomenon that should follow a specific statistical distribution. For example, a hole diameter is expected to be randomly distributed around a mean. This mean typically corresponds to the center of the specification for this diameter. And this is the description of a normal distribution. The part flatness, being the absolute value of the difference between two measurements, is expected to follow a Weibull distribution. The values are concentrated around 0, with then a long tail of highest values. And the distance also between a reference position and an observed position based on X and Y Cartesian coordinates is expected to follow a Rayleigh distribution. So if we go more in the details and we look at the hole diameter, so this is an example, and it shows an extraction of different diameters over the time. And on the run chart, we don't see any specific pattern, and the distribution plot confirms that the data are normally distributed. For this distribution, we have plotted different IGCs based on different requirement levels. These levels are directly linked to the process capability. And of course, the higher the capability level, the wider the IGC. If we look at the next example about the flatness, on the run chart, in that case also, we don't see any specific pattern. And as you can see, the data follows a very clean Weibull distribution because, in fact, the data was simulated. So values that are concentrated around 0, and then this long tail on the highest value direction. And we also plotted different IGC levels. In that case, as all the values are positive, we don't have a lower limit, and we are focusing only on the higher limits, and we see directly the impact of the requirement level on the IGC. So far, I focused only on simulated data, but the next question is how we apply this to real data for a robust IGC estimation. And to answer that, I'll hand it over to Sophie.
Thank you, Caroline. So to perform a robust estimation of the IGC and real data, it implies 4 steps. The first step, which is the most obvious one, is to collect data. In the case of Airbus, we are collecting data from their data lake, which is called Skywise, but we can also collect data from simple text files. For instance, here you have a screenshot of how the data looks like in the case of our analysis. So it's the typical format for data with information such as the product, the entity, the instrument name, the characteristics, and so on. When we have the data, the second step is to check the data, clean the data, because we cannot go straightforward in the analysis. We first need to check the data. So to do that, for instance, we can look for outliers. If you look at the picture you have at the right, you see it's the old diameter, and we have clearly outliers at the value of 3, which is an incorrect entry in our case. So we will remove it from the analysis to not pollute our analysis. So this is the first thing we can do to clean our data before the analysis. Next thing we can do is to select a stable period of time on which we will do the IGC analysis. For instance, again, you see the process in the picture vary a lot at the beginning, and after, for some reason, it is stable. We will do the analysis on this stable period of time because it represents the real variety of the process. And finally, final thing we can do in our case is to check if the data distribution is unexpected. So this step is very important because in our database, we know for each parameter what is the expected distribution, like normal, Weibull, Rayleigh, like mentioned Caroline and Hélène earlier. And this step is very important because depending on the expected distribution, the calculation of the IGC is different. So we need to check if the distribution is the one we expect. For instance, you see the old diameter is expected to be normally distributed. So in JMP, we can just fit a normal distribution and do a classical goodness of fit test to check if we can validate the distribution or not. If we can validate the distribution, we can go to the IGC calculation. Otherwise, we need to investigate more why the expected distribution is not validated. Maybe there's some outliers, some reason to investigate. The third step is if all the assumptions in the cleaning data were validated, we can now go to the calculation of the IGC. So here in our case, you see we are calculating three IGC, IGC1, IGC 1.33 and IGC 1.67, calculated like Caroline and Hélène explained in the presentation earlier. And once all of this is done, we want to save the results because maybe in a future analysis, we will use this result. So to do this, we store the result we have in a new database, AWS database called MCDB. Currently, all of this was done manually, and our objective now is to automate this in JMP directly in the application that Julie will show you in a live show.
Yes, thank you, Sophie. So I will first introduce you to the example. So we have this part that is a simulated one with simulated data. That is representing well the type of parts that we are analyzing in Airbus, and we have fake requirements on it. And I propose to share my screen and to show you a little bit how we can analyze these parts directly into JMP. So here we have the home window of JMP, and we can open directly the add-in that has been developed by Innovipon, and we can start an IGC assessment. So we give the study a name, and we can select the entity we are working in and our team, and then we can create the study to first extract the data. So as explained by Sophie, we can either extract it manually with text files or via the data lake extraction. So here we will use the text file extraction, and we will arrive onto the next page automatically, which is the cluster page. On this page, we will have a list of automated created cluster. A cluster is a set of measurement data that can be analyzed together in order to, that is statistically relevant, in order to have enough measurement points to be robust statistically. Here, for the demo, we will use the automatic generated clusters by the add-in, and we will run the IGC analysis on all of them. After some time of loading, we will have the IGC assessment page, which is a dashboard that has been developed to follow the same process as Sophie explained. So as you can see, first is the distribution area where the goodness of it is performed, where you can see the distribution charts. And then the second step is to have a look at the control charts and AWMA charts. So here it's in this area of the dashboard. And finally, down below, we have all the statistic indicators, including the IGC, which is the output of the add-in. And we have the IGC for CP equals to 1, 143, and 167. And finally, we have the summary of all the clusters in here. So I propose for the demo to go over all the clusters that we have. So the first one is supposed to be a normal distribution on a position requirement. Here we go down below, we see that the expected distribution is effectively normal and the goodness of it has been accepted. We have a good looking distribution chart, and as well with the control chart, nothing is abnormal. We have the IGC calculated, and as well, because of all statistical indicators are on the green, it has been already validated automatically by the add-in. Same principle onto the next cluster for a Weibull distribution for flatness. So same example as Caroline already explained. So the Weibull has been accepted automatically for the goodness of it. The control chart looks good. We don't have any abnormal data in the IGC, in the control chart, and the IGC is good. It has been validated automatically as well. So we can go on to the next one. So here we have a cluster that is supposed to be a normal low on a surface profile, so with positive and negative values. However, even if the normal goodness of it has been accepted, we can see that on the control charts, we have strange behavior with what looks like 2 steps or a deviation that went back to normal. And what is important here is to check the physical phenomenon behind that. So by asking around in the production center to know what happened. And once you have checked that is in fact abnormal data, you can select it onto your control charts and exclude it for the assessments. automatically, by doing that, all the statistical indicators have been updated, including the IGC. And since everything looks normal now, we can change the validation status to validated and update it into the summary table. Now going on to the next cluster, which is supposed to be, we don't know, to be investigated. We have a surface profile, again, with positive and negative values. And it looks like it should be a normal law, like the one we saw just before. The normal goodness of it has been accepted. We have a good looking distribution chart as well as a control chart, but we have one thing is here we have something that looks like a deviation. So after checking with production again and the physical phenomenon, we can exclude those data because it is in fact abnormal and not representing the process as it is in fact. Once everything is done, we have to validate that is really a normal distribution, validate it, and now the statistical indicators have been calculated. We can validate this cluster and update it into the summary table. Moving on to the next one, we have as well a to be investigated expected distribution. It means that it has not been in the data sets, input data sets, it has not been informed which one is it, so we have to investigate. We have a requirement that is supposed to be a position with positive only values, so it is what looks like a relay distribution. So all goodness of fits have been accepted. The control chart has nothing abnormal in it, but for the moment the IGC has not been calculated. So if we validate the relay distribution because it is following the physical phenomenon, we have the IGC that is being calculated and we can validate our study. Moving on to the next cluster, we have some goodness of fit objectives, especially on the relay distribution, which is the expected one. So we have to investigate why, and by going on to the control chart, we quickly see what is happening. We have two outliers here detected, and in this case, we can exclude them after checking for the physical phenomenon. And now we have the relay distribution that has been accepted, and we have the IGC calculated. So we can validate it and go on to the last cluster. So the last cluster is supposed to be a normal distributed data on a line profile with two tolerance feature name, meaning that on the part that you saw previously, we are measuring one side of the part and the other one on the same requirements. So when we have a look at this, we quickly see that there is a problem on the distribution and that it seems to follow two underlying normal distributions, meaning that when our two tolerance features measured have not the same decentering, which is meaning that we cannot analyze those two tolerance features together. So to resolve this issue, we can go back to the cluster settings that I showed you before and go on to this cluster and see, okay, we have two tolerance features that are corresponding to those two here. So we are selecting the first one and creating a cluster on this single one. And then the same for the edge 2, creating a new cluster. And if we go back, so the two have been added to the cluster list. We can select the three of them and run the analysis only on those selected ones. And now we can compare and see if creating those 2 new clusters is solving the issue. Directly, we can see that it has been validated automatically by the add-in, meaning that it seems to have resolved the issue. If we go back to the details, we see a better distributed data with a better control chart. So everything looks good. And to go back on the faulty cluster, we can not validate it by choosing this status and update to the summary table. Now that this has been done, we have all the clusters that have been checked, validated or not validated, and we can click on to export IGCA results to database, and this will send all this analysis to AWS and to continue the study in the MCDB application. I will now hand over to Hélène so that she can do the conclusion.
Thank you for the demo, Julie. To conclude, let's have a look at the result. We now have a user-friendly tool that makes assessing geometrical capability fast and consistent, but it is not just only a tool for Airbus. We have also aligned our working method. So this shift gives us more confidence in our data, which is essential for making the right decision when setting tolerance in co-design. Moving forward, we will scale up through team training, and we already have further updates planned for the tool. This brings us to the end of the presentation. Thank you for your time and your attention.